We've spent quite a number of days now finding the net force or the acceleration when there's multiple forces acting on an object, whether it's a straight one-dimensional problem with somebody pulling to the right and somebody pulling to the left, or whether it's an inclined plane or an elevator problem or a pulley problem. Okay, they all boil down to pretty much the same thing. But what if we have a two-dimensional problem? What if we have a force acting on an object this way and then a force acting on an object this way? How do we deal with that? Well, we still have to add the forces together, but this time we have to add the forces together in x and y components, which is real similar to what we did when we added displacement vectors together. So the method that you're going to see here over the next few minutes and the example that you're going to see is going to be, in a sense, different than what we've done before, but in a sense, almost the same as what we did back in our last unit. Let me outline the steps for you in solving one of these problems. The first step is to draw a free body diagram. Just like it was in the one-dimensional problems, draw a free body diagram. Whenever we have more than one force acting on an object, we draw a free body diagram. Now, if forces cancel out because they're equal and opposite, that's wonderful. And in fact, if forces cancel out such that you only have forces in one dimension left, great. You get a problem like we've been dealing with for the last 2 weeks. But if forces don't cancel out and you're left with forces in 2 dimensions like this, then you've got to continue on with this method. So number 1, draw your free body diagram. Number 2, if they don't cancel out, then find the x and the y components of the vectors. Find the x and the y components of all the vectors. The x component of this vector right here, vector number 1, easy. The x component of vector number 2 and the x component of vector number 3 here, not so easy because those are at funny angles. But we know what to do with that, right? We don't like funny angles. We take them off to the side, we resolve them into x and y components, and then we deal with it. So find the total x components and the total y component. The x component of vector 1 plus the x component of vector 2 plus the x component of vector 3. The total x component. The y component of vector 1, the y component of vector 2, the y component of vector 3. Add them up, get the total y component. So get the total x and the total y components of all the vectors. And then you're going to draw a right angle vector diagram and find the resultant vector. So once you get all the x's, all the y's, redraw it as a right angle triangle, just like we did when we were adding displacement vectors in our last unit. The only difference is it's going to say newtons on the end of these instead of meters on the end of them. Now, once you've got a right angle vector diagram and you find the resultant vector, you're done. How are we going to find the resultant vector, though? Well, the Pythagorean theorem and the tan function gives us the angle, just like it did back in our last unit adding displacement vectors. Let's do an example. It's the best way to show you what this stuff really means here. Do an example. The example is in your notes. Example number 10, it says a 10-kilogram bag of candy is pulled to the north with a force of 200 newtons, to the south with 50, and at an angle of 30 degrees west of north with a force of 100 newtons. What's the net force acting on a bag of candy? So I'm gonna draw the bag of candy here. It's 10 kilograms. It's pulled to the north with a force of 200 newtons. I'm going to call that F1. 200 newtons. It's pulled to the south with a force of 50 newtons. It would be nice if that force to the south was exactly the same value as the force to the north. How come? Because then they would cancel out, right? And then I could only have one force left. We're going to call this F2. Its value is 50 newtons. They don't cancel out, so far that's okay. Still, so far, I have a one-dimensional problem, right? Where you just say F net is equal to the sum of the forces. But as soon as I draw this one in, this 30 degrees west of north, I'll call that F3. It's 100 newtons, and it's 30 degrees west of north. As soon as I introduce that, now I've got a two-dimensional problem. Forces don't cancel out here. I've got to deal with the x and the y components. So first thing I see here, honestly, the first thing I see before I even do that recipe is to say I don't like funny angles. Take the 30 degrees off to the side here and deal with it. This is x, this is y, this is 100 newtons, and this is 30 degrees. We're going to say cosine 30 degrees is equal to x over 100. X is equal to 86.6 newtons. And sine 30 degrees is equal to y over 100. Y is equal to 50 newtons. There's my little off to the side thing. Now, I think what I'm going to do here is actually erase that 100 newtons because, remember, it's dead to us. We never want to see that 100 newtons again, right? We're never going to use it. We resolved it into x and y. Let's just get rid of it. We have an x that's 86 newtons, 86.6 newtons to the left, and we have a y component that's 50 newtons up. Yep. Is it the other way around? Oh, it is. Oh, it is. Good thing I made that mistake on purpose to test to see if you were noticing. Bernardo noticed. Good. What's wrong with what I just did here? Cosine 30, cosine is the adjacent side, right? And that's the y component of this one, right? So we're going to say that this 86.6 is the y component, and this 50 newtons is the x component. Does that make sense, guys? I didn't make that mistake on purpose. You see how easy it is to do that, right? Okay, that was a legitimate mistake. Okay, I hope that if I was doing this on a test that I would check over my work and catch that. I hope. Okay, but it's easy. It's easy to make that mistake. So we're not going to replace that with an 86 and a 50. We're going to replace it with a 50 and an 86. 50 to the left and 86.6 up. So step one was draw my free body diagram. I did that, and then I simplified my free body diagram by resolving my vectors into x and y components. Well, now I'm going to say x components and y components. The x component of the first one is what? Enrique, how much of that 200 is x? 0. Okay, how much the x component of the second one is? 0. The x component of the third one, anybody? Dexter, what's the x component of this third vector? Negative 50, good. So we add those up and we get negative 50 newtons. Now the y component, we got 200. What's the y component of the second one? Mackenzie, what's the y component of the second one, F2? Good, negative 50. And what's the y component of the third one, Tara? 86.6, good. Okay, we add those up, and we're going to get, what, 286.6 minus 50 is 236.6? Is that right? Yeah. That was step 2. Find the total x, find the total y. And then I'm going to redraw it. I get 50 newtons to the left. I've got 236 up. And then my resultant vector right here, which is the sum of the vectors, is just going to be found by the Pythagorean theorem. Is this ringing a bell? We've done this, like we've done almost this exact question before. Imagine if I said, guy walks 200 meters to the north, then he walks 50 meters to the south, and then he walks 100 meters at 30 degrees west of north. Find his displacement. You do this question exactly the same, right? Exactly the same, except it wouldn't say 50 newtons, 200 newtons, 86 newtons. It would say 50 meters, 200 meters, 86 meters. Other than that, it would be exactly the same, right? Exactly. Let's find the value of r here. We'll do this one as a group here. Let's say the square root of 236.6 squared plus 50 squared gives me a value of 241.8, or we're going to round that to, I think, 2 digits. Yeah. 2.4 times 10 to the 2 newtons. And theta is the inverse tan function of opposite over adjacent, this case 236.6 divided by 50. Theta is going to be 78 degrees. That would be 78 degrees north of west.